this carbon snake demonstration, we will be combining sugar and sulfuric acid to produce carbon, water, and a mixture of water and acid. Here is our sulfuric acid, sugar, and a beaker to combine them in. After adding the sugar, we will carefully add the concentrated sulfuric acid. As the sulfuric acid incorporates with the sugar, we can see a color change starting to occur. Stirring to incorporate all acid with sugar will speed up the reaction. The substances begin to bubble and finally have enough energy to release some of the water produced in the form of steam, along with some other gases such as carbon dioxide. We can now recognize the black snake, which is carbon in the form of graphite. Heat is also produced, indicated by the hot steam emitted from the carbon as well as from the hot temperature of the beaker. The graphite is very messy, and one must neutralize the remaining acid with baking soda to clean up. Dehydration occurs in this reaction when the sugar is dehydrated by the sulfuric acid, producing carbon and water. The reason the reaction creates a black snake is because graphite, which is the black solid-like substance, is produced by the dehydration of sugar. There are 3 reactions occurring in this demonstration. Note that the sulfuric acid is not included, and this is because it is a catalyst, so it is not used up and reappears at the end of the overall reaction. The first reaction is the dehydration of sugar. This is an exothermic reaction, which means that it produces heat. An exothermic reaction has an enthalpy lower than 0 or a negative enthalpy. Reaction 1's enthalpy is calculated by subtracting the standard enthalpy of combustion in reaction 2 by 12 times the standard enthalpy of formation of the carbon dioxide in reaction 3. We can do this because standard enthalpy of reaction is equal to moles times the standard enthalpy of the formation of products minus moles times the standard enthalpy of formation of the reactants. The product we are interested in is carbon and the reactant is sucrose. Therefore, we can rearrange equations 2 and 3 to find that the standard enthalpy of reaction 1 is equal to negative 918.9 kilojoules per mole. Because its standard enthalpy is negative, the reaction is exothermic and produces heat. This explains why the beaker was so hot after the reaction occurred.